Go over an Aldol problem, specifically predict the product and draw the mechanism. If we have time, I also want to do another problem where we have to predict the starting material that gave an Aldol condensation product. Let's do this one by one. The first problem will be draw the Aldol product and its mechanism. Probably for my class, I'm not going to give a hint. It's an Aldol product. I'll just say draw the product and mechanism. The problem that I have written down is this. Here we start out with a ketone. The aldol can start with an aldehyde or a ketone. We need an oxide base. It doesn't matter whether it's hydroxide or ethoxide or methoxide. There's definitely going to be some protic solvent because there's going to be a protonation at some point. Now, this is important depending on what textbook and what professor you have. Some professors want you to go all the way to the conjugated system. Others want you to stop at the aldol, which is the beta hydroxy carbonyl. I want my students to assume that you'll go all the way to the conjugated system, which is fairly stable, and that would be my final product. For professors who want to break it up into the aldol and the aldol condensation product, typically they would specify that with heat. Like you would see heat here, and then you would go to the conjugated product. But not for my class. I could have heat, definitely go to the conjugated product, or no heat, you would still go to the conjugated product. Okay, I know that was a lot to digest. Let me draw you the final product if I was to give this problem. Draw the starting material as is, I typically say, and mark the alpha. Now I did swing the methyl group downward because I want to make a connection between that alpha carbon and the molecule that it attacked. So the molecule it attacked was another one of itself, and the point of attachment would be at the alpha carbon. It doesn't matter which one you use because it's symmetrical, so the point of attachment would be there. You can imagine what happens to that carbonyl group. You'll kick up. We're not drawing the mechanism just yet. I'm just showing you the strategy. So let me just put it in dotted arrows. Okay. Now, I'm thinking ahead. The final product is conjugated. And so initially we had a hydroxyl group here. But when we do a dehydration, we move that OH and the H that's here, we get a double bond. Okay, so let me draw you the final product. If you need to put a little dot to orient where you are, there's a double bond between the alpha and the dot. Look what else is attached to the dot. We have two alpha groups. So again, even without heat, this is your final product. And so for my class, I'll put here in parentheses, with or without, always try to draw the conjugated product, with or without heat. Okay. Just real quick, because I don't know if people realize this, conjugation means that you have a double bond, single bond, double bond alternating pattern, but that's unique because did you notice that 4 atoms in a row, they're all sp2. That's what makes something conjugated, where you have a row of sp2 atoms. Later on, maybe in a different video, I'll explain why that's stabilizing. It has to deal with the idea that each of those atoms has an unhybridized p orbital that can overlap with its neighboring p orbitals, and you can spread out the electrons a lot better. So we need this alternating double bond, single bond pattern. Okay, let me draw the mechanism. The mechanism starts out obviously with the ketone. And let me draw the two alpha hydrogens on this side of the molecule. Let me draw the alpha out of the way. Let me draw it there. Obviously, you don't have to draw alpha. I just want to mark it so I know, remind myself like which hydrogens are acidic. Okay? It's not random that we take off one of those protons. It's intentional because those are the most acidic due to resonance. Okay, so again, it's all about where you're getting your information from. I think I like my way because it shows you the major contributor. A lot of people, not a lot of people, but a lot of sources have the anion on carbon and they do this, put the negative charge there. It's fine, it's a resonance contributor, but it's not the major contributor. The major contributor would be the negative charge on the oxygen. And so I like to draw the major contributor. And I have here O minus. We have a double bond. It doesn't matter. You'll have a mixture of cis and trans. I'll just draw it cis or downward on the same side as the ethyl so I can make the attack to the upper right. We did create water plus H2O. And so now our next step, the second step, is we attack another one of itself. Did you notice that this is the enolate and this is the non-enolate? So we do need an equilibrium between the enolate and the non-enolate. If you have a super strong base, you'll get 100% of the enolate and you'll have nothing to attack. Okay, you can remember that enolate does not attack enolate. You have to attack a non-enolate. Okay. It makes more sense because, an anion is less likely to attack another anion. It's more likely to attack a neutral molecule. So remake the double bond, forces this pi bond to break and attach to this carbon, and we have that. If you're wondering where that orange dot is, it's this one right here. Okay. We are headed towards 5 steps, I believe. So this is step only 2. Let me redraw this double bond better. Okay, single bond here. Yes, single bond there. O minus here. 2 alpha groups. And let me mark the alpha. Let me mark it here. And let me mark the dot. Again, all of this alpha and dot markings, those are just annotations that I think are helpful, not necessary for the mechanism. We created water here. We also have water up here. Let's do the protonation. Okay, super, super important. Some students are still writing H3O+. But the thing is, you're under basic conditions, you will never have H3O+. And so the general rule that I tell my students is there's no O+ when you're under basic conditions. Just like there's no O- under acidic conditions. So don't protonate with H3O+, protonate with water. That is your Aldol product. What did we kick out? We created a OH-. So this is interesting because we have now base nearby. We just created more base. And we do have a fairly acidic hydrogen now here. It's still the alpha hydrogen and it's still acidic. So we are going to strip off that H, the acidic hydrogen, and we're going to form the second enolate, or another enolate. Okay? Do not kick out this OH yet, okay? The mechanism does not kick out the OH at this step. You first have to form the enolate, or you can think of it as the conjugate base, right? Isn't this deprotonation? So when you deprotonate something, you make it the conjugate base. There is evidence that this happens. By paper, it would have been awesome, right? It would have been awesome to make that and then kick this out. But that's not how it works in real life. There's evidence that you form another enolate intermediate. Okay? And then we eliminate the OH minus. It's an unusual mechanism. We are doing a dehydration, okay? And from Organic Chemistry 1, you know about acid-catalyzed dehydration of alcohols. But this is not acid-catalyzed. And we separate the steps between the deprotonation and the kick out of the leaving group. When you have those separated, when you have those as two different steps, it's E1. Remember E2? E2 is a fast one. You grab the proton and kick out OH at the same time. When you separate them, it's E1. But it's a special type of E1 called E1CB, E1 conjugate base. So this is your conjugate base. And we did eliminate the OH at this point. This is called E1 elimination unimolecular conjugate base. Unimolecular, right? Unimolecular because, see, I am not using any other molecule to kick out the OH minus. Remember unimolecular and bimolecular? So I'm just trying to tie in some of these concepts that you've heard of in the past because they come back. Organic chemistry builds upon itself. For some, that makes Organic Chemistry 2 much easier because they have all this information on Organic Chemistry 1 that's helping them. But if you treat them as two different courses, man, Organic Chemistry 2 is a beast. If you're not remembering some of the things that you learned from Organic Chemistry 1. Okay? Did I promise you 5 steps? 1, 2, 3, 4, and 5. Okay. I call this a self-Aldol condensation. Condensation because we made the double bond. Condensation because we release water, right? Did we release water somewhere? We had water here. Okay. So we release water. So that's self-Aldol condensation. Okay. Think about that. Excuse me. All right. There is one other problem that I wanted to fit in onto this video. Yikes. I want to go backwards. Yikes. I want to give you the product, and you tell me what the starting material is. If we think about what reaction we just did, we had this ketone, base, H2O, heat or no heat. I want people to draw the conjugated system. Oh, there's a caveat. Draw the conjugated system if it's possible. It would not have been possible if there was no hydrogen here in the alpha position. But it is possible in this case. Oops, and we have this. We have the alpha. We have the dot. Technically, the dot is now the beta. And I redrew this because I want us to develop a strategy to go backwards where we don't have this. Okay? And the strategy is this. We have to realize that the bond that was made was this bond right here. And this dot, by the way, had a what on it? This dot used to be the carbonyl. So can you see that this really came from one of the ketones being the enolate and one of the ketones being the attacky. And look how I drew it. Okay, maybe this will help as well. See, if I just put this right here, and there's a bond between these two, that's going to be a little bit tricky. But let me go back. So do you see how I drew this piece and this piece with the same, I guess, orientation? All right, enough of that. Let me give you your products and you tell me what the starting materials were. Are you to assume that these are self-Aldol condensations? Don't assume that. Do the green dotted line and ask yourself, did it attack another one of itself? Or did it attack another aldehyde or ketone which would be actually a cross aldol? This one, the second one, is a little bit tricky. So try to make it easier on yourself and redraw it. Okay? The answer for the first one is, you see the carbonyl? It's that piece that did the attacking. So go ahead and find the alpha. This is now the beta. And yes, this is your disconnect. So it is true that we had this ketone became an enolate and attacked this ketone here, which is identical. Okay. For the answer, though, since they're identical, just draw it once. Okay. And you know that the reaction is this. NaOH. Oh, heck. I was about to write NaOET, so same difference. But your solvent, it's just good practice to make it match the R group. And heat or no heat, it doesn't matter to me. This will occur, I think, without heat also. For the last one, redraw. And maybe you'll notice that, maybe this is also a self-aldol. It's hard to tell. But you could hopefully assume that this is your alpha, right? It's alpha to the carbonyl. And so I think one of the starting materials looks like this. And the other one was an aldehyde. Okay? Draw your green dotted line to prove it to yourself. Isn't that beta carbon originally the carbonyl? See how this beta here was originally the carbonyl? That beta was right here. So there's a carbonyl. When it got attacked, it became now the beta of the whole molecule. Okay? And yeah, look at this. 1, 2, 3, 4. 1, 2, 3, 4. It is the same molecule that attacked one of itself. 1, 2, 3, 4. And let's use NaOH in this case, and water. Okay. So there you have a simple fill in the product, the mechanism, 5 steps. By the way, if you do a intramolecular aldol, it will also be 5 steps. And if you do a cross aldol, and you use an oxide base, it would be 5 steps as well. It might be different if you use a super strong base and in your cross aldol. That's the example where you use LDA. Maybe we'll go over that in a different video. But please, this is the basics, okay? You have to know how to draw the aldol product, especially a self-aldol product. And let me be super specific. Self-aldol condensation product. And be able to draw the mechanism. One step above that is if I give you the final product, would you be able to decipher what the starting material are?